This video is about hyperbolic functions and their derivatives. As always, begin by reading carefully through the textbook and taking some good notes, but now consider the following highlights for this topic. In terms of the definitions for these hyperbolic functions, which will be provided on assessments, we don't have to memorize these, the following foundational functions exist. So sine hyperbolic, typically denoted SINH, and sometimes pronounced informally as sinh, is equal to a fraction whose numerator is e to the x minus e to the negative x, and that's all over 2. Secondly, cosine hyperbolic, abbreviated or listed as COSH, sometimes pronounced informally as cosh of x, is a fraction whose numerator is e to the x plus e to the negative x all over 2. Those two foundational functions or definitions for sinh and cosh will then help build the rest of them. In fact, if you look carefully through a textbook on the definitions of these, you'll find that these hyperbolic functions are related to the hyperbola in the same way that trig functions are related to the circle. So you'll notice or observe what seems to be some kind of blending of algebra and trigonometry with these functions. Moving on then, tangent hyperbolic, sometimes shorthand said as tanh, T-A-N-H of x, is equal to sinh over cosh. And again, that resembles the trigonometric definition for tangent being sine over cosine. So there are some familiarities there. Moving on, cosecant hyperbolic of x is equal to 1 over sinh, or sine hyperbolic of x, which of course resembles the trig identity or trig definition for cosecant. Secant hyperbolic of x similarly equals 1 over cosine hyperbolic of x, or 1 over cosh of x. And lastly, cotangent hyperbolic of x is equal to cosh over sinh, cosine hyperbolic of x over sine hyperbolic of x. Again, these resembling their counterparts in trigonometric definitions and identities. There are some hyperbolic identities which will be provided, so don't have to be memorized, that also represent or resemble, I should say, some trigonometric identities. For example, sinh of negative x is equal to negative sinh of x. That resembles the negative identity for sine in trigonometric identities. Similarly, cosh of negative x equals cosh of x, resembling the negative identity for cosine in trig. Moving on, cosh squared of x minus sine hyperbolic squared. So cosh squared minus sinh squared of x equals 1. Now that does look similar to some trig, but you'll notice this one has a minus instead of a plus, which is what we're used to seeing in the Pythagorean identity of trigonometry. Moving on, 1 minus tangent hyperbolic squared of x, so 1 minus tang squared of x is equal to secant hyperbolic squared of x, again resembling the trig identities that would involve tan and secant. And moving on then next, we'll say in some sum identities or addition identities, sinh of x plus y, a sum of inputs, is equal to sinh x cosh y plus cosh x sinh y, or similarly, cosh of x plus y is equal to cosh x times cosh y plus sinh x times sinh y. So these, again, don't have to be memorized. They'll be provided for you on an assessment, but I'm just defining them so that we're familiar enough to use them, which is really the purpose we have right now. Now in calculus, moving on, of course, we're going to also understand their derivatives. And so for some derivatives of hyperbolic functions, also provided, not need to be memorized, we have the following, and these should look somewhat familiar if you correlate or compare them to trigonometry. So the derivative of sinh, that is sine hyperbolic of x, is equal to cosh of x, cosine hyperbolic of x. Or similarly, the derivative of cosh of x is equal to sinh of x. Now you'll notice a subtle difference there. If you go back to basic trigonometry, the derivative of sine is cosine, so that looks familiar to us. But in trigonometry, the derivative of cosine is negative sine. So we're seeing a difference here now where there's no negative sign that is negative symbol in front of the sine hyperbolic function. Moving on, the derivative of tanh x would be equal to secant hyperbolic squared of x. There's some familiarity there because the derivative of tangent would be secant squared in trigonometry. Moving on, the derivative of cosecant hyperbolic of x is negative cosecant hyperbolic of x cotangent hyperbolic of x. Next, the derivative of secant hyperbolic of x is equal to negative secant hyperbolic of x tangent hyperbolic of x. And lastly, the derivative of cotangent hyperbolic of x is equal to negative cosecant hyperbolic squared of x. So again, it's fun to look for similarities that might help you remember or see the resemblance between these in some trigonometry or some actual differences they have, but these will be provided, so no need to be fretting about memorizing every one of these. But it's good to use them, and that's what we're going to do next with some examples. Let's now work through some examples here. Our first set says find the numerical value of each expression, and our first expression given is cosh, so cosine hyperbolic, of natural log of 5 as our input. Now, if you glance back up at the definition for cosh, or cosine hyperbolic, you'll notice that it's really defined as a fraction whose numerator is e to the x plus e to the negative x, and then it's all over 2. So let's simply plug this in where we know our denominator is 2. I'm going to write that as our denominator of a fraction, but the numerator is e to the x. Well, x is our input in this problem given as natural log of 5. So our numerator is going to be e to the natural log of 5, abbreviated ln of 5. And then we'll say plus as part of the definition, and then it's e to the negative x, which would be negative ln of 5 for this given input of natural log of 5. Now, we want to simplify this to the best of our ability, so let's do a little bit more with this one. Starting off, we can recognize a couple familiar algebraic expressions here. So if we go to, for example, this numerator and look at e to the ln of 5, that is e to the natural log of 5, we can recognize that e to the ln power, those reduce. This is just 5. E to the ln of 5 is just 5. You recall from just algebra, maybe pre-calc, that would be the case to reduce that. Now, you may look at the second term in the numerator and say, well, that one doesn't quite fit the same reduction because it's not e to the ln, it's e to the negative ln. True. So we can do a bit of algebraic work on this one to make it look a little bit better. So in our next step, we're going to convert that first term in the numerator just to 5. Then I'll put a plus sign, which would come, of course, between these terms. For the second term, we're going to do a little bit of an algebraic trick here, which is I'm going to rewrite that instead of e to the negative ln of 5, we're going to write that as e to the ln of 5 to the negative 1 power. So I'm going to write e to the ln of 5 in parentheses and then give that a power of negative 1. We know that with exponent rules, this is all equivalent, right? You'd be multiplying these powers together, and of course, the negative 1 times the natural log of 5 would give you the negative natural log of 5 that you started with there, right? So that's all equivalent, but this is now more user-friendly. And of course, this is all still over 2. Now let's take another step in this. So our numerator has the first term of 5. That's going to stay as is. But then now for our second term in the numerator, we have e to the ln of 5. Well, that's also just 5. But now that was in parentheses raised to the negative 1 power, so we should keep that as is, and this is all over 2. Now we can do a little bit more simplification with this, so let's keep it going. Just using, again, basic algebra here. This is 5 plus 5 to the negative 1 power is 1 over 5, or 1 over 5 to the positive 1 power, right? And that's all over 2. So we can do some more simplification on this, but it's getting a little bit better already. Just doing a little bit of arithmetic in our numerator here, moving on. We have 5 plus 1/5. Well, we know that's really 26 fifths. Just doing some arithmetic there. And that's all over 2, so you could really call that times 1/2 if you want to get the fraction simplified a little bit more there. And then, of course, reducing this 1/2 times 26 over 5 would end up being 13 over 5 by reducing the 2 and 26, which is where we finish. We can't get any simpler than that. It's a reduced fraction. It's improper, and we'll leave it just as that, 13 over 5. We were asked to find the numerical value of each expression in our instructions, and that's exactly what we found. There's no need to turn it into a decimal there. Our second example in this same set of instructions, so part B, is beginning as cosh of 5, that is cosine hyperbolic of 5. Well, let's recall the definition for cosine hyperbolic and simply plug in 5 as the input as given. So of course, cosine is defined as a numerator, which is e to the x, so now that would be e to the 5, plus e to the negative x, so e to the negative 5, and then it's all over 2. Now this one's not going to get much prettier in terms of simplification, and since we're only trying to find the numerical value of each expression rather than an exact value, maybe where we would leave the e in it or something like that, we're just going to estimate this using a calculator. So take out your graphing calculator. I'm using a TI-84 Plus here, and we're simply going to punch this expression in. Now be careful with that as always. So our numerator has to be in parentheses, and we'll, in our numerator, type in e to the x, but instead of x, we're going to put 5 because we have e to the 5th as our first term. Then we have plus, and then is e to the negative 5. So we'll again punch in an exponential expression. So e to the negative 5 power. We're just plugging this in pretty much as we wrote it into the calculator. Of course, then we'll divide by 2 since that's what we have. All divided by 2, hit enter, and we get a value of 74.20994852. Okay, we're going to round this to something. Now, we didn't have any specification on what to round to here. If you, of course, do have that, like instructions on what to round to, then follow them. I'll just round it to the nearest hundredth, 2 decimal places here, and call this 74.21. Let's move on to a second example. This next one states, write the following expression in terms of e to the x and e to the negative x. Now the expression given is as follows. It says write 8 sinh x plus 5 cosh x in terms of e to the x and e to the negative x. Now what we know from our definitions above is that those functions are defined in terms of e to the x and e to the negative x. So we simply want to bring in those definitions that we have above, but with a couple extra little pieces involved. So for example, our first term given is 8 sinh x. So that means we're going to put an 8 in front of the definition for sine hyperbolic of x. If we look above at that definition, we're just going to copy it in here, which is of course e to the x minus e to the negative x all over 2. So we have 8 times the definition for sine hyperbolic of x as our first term. And we'll do the same kind of thing for our second term. So we'll just say plus, which is part of the expression given. And then it's 5 cosh of x. So we'll put it in as 5, and then in parentheses, the definition for cosine hyperbolic of x, which would be e to the x plus e to the negative x all over 2. Now, I suppose you could argue at this point that we've written this expression in terms of e to the x and e to the x and e to the negative x, which is what we're being asked to do, therefore we're done. But we should also make it algebraically simpler. It would be more appropriate to simplify. It's not much. If we distribute the 8 to the first term and the 5 to the second term, and then consider that they're all over 2, we can get this looking a lot better. So let's do that. For the first term, I'm going to write this as 8 over 2 e to the x, which would be simply distributing the 8 and then recalling or noticing it's over 2. So it's 8 over 2 e to the x minus 8 over 2 e to the negative x. That's just distributing and simplifying that first term. Moving on in the same way, we'll say plus 5 over 2 e to the x plus 5 over 2 e to the negative x. Again, just distributing the 5 to the numerator and then considering that we're dividing by 2 in both terms. Now, what we'll notice here is that we have some like terms to combine. So you'll notice, for example, that we have e to the x terms. There are two of them, and they are like, so we can and should combine those. And then similarly, we have e to the negative x terms, two of those, and we should combine those as like terms. And that's all we'll do to finish. So we'll write this one more time, then as equals. For my e to the x terms, I have 8 over 2 plus 5 over 2, which would be, well, 13 over 2, e to the x. And then for the negative x terms, we have a negative 8 over 2 plus a 5 over 2, just combining those like terms. So negative 8 plus 5, of course, gives us a minus 3 over 2, and that's e to the negative x. So minus 3 halves e to the negative x. And that's better than it was. It's still in terms of e to the x and e to the negative x, and so we'll finish right there. Moving on to our next example, it states, prove the identity. Now, this may sound familiar to trigonometry if you think back to those types of problems. And we want to prove the identity given as tanh of natural log of x, that's the left side, and that is equal to the right side, which is a fraction whose numerator is x squared minus 1 and whose denominator is x squared plus 1. Now, we can assume that this identity is true as given. What we want to do is prove it. We want to be able to start on one side and get to the other. Now, as you may recall from trigonometric problems like this, a good strategy is to start with the more complex or complicated looking side, though that can be open to interpretation. In this case, if we take that kind of approach, I think it's helpful to start with the tanh, since that's the more complicated function. The right side is a pretty simple algebraic expression. So let's start with the tanh of ln of x and see where that goes. If I simply start there by writing it out, tanh of ln of x, and then let's use the definition we have for this. So we know that tanh is equal to sinh, so sine hyperbolic of the same input, natural log of x, over cosh, cosine hyperbolic of same input, natural log of x. Again, these are just referring to the identities we have above. You can glance back up at those just to refamiliarize yourself with them, but that's all we're doing. We're plugging in what we know. Tanh is equal to sinh over cosh for the given input. Now, if we take this a step further, let's use the definition of sinh and cosh as given above with the inputs of natural log of x, which is what we have in this problem. So what that means is the numerator, instead of just being sinh of natural log of x, the definition for sinh is e to the input, so we want e to the ln of x with that input, minus e to the negative input, so e to the negative ln of x. Again, that's just using the definition of sinh provided above. Of course, it's all over 2, so we should make sure, let's see, we can just put a 1/2 outside of that one to make sure that's still part of what we have. It's going to cancel out in a second, so don't worry about that, but you'll see. Below it, we have cosh of natural log of x. Well, again, using that definition, we would have e to the natural log of x plus e to the negative natural log of x, and of course it's all over 2. We should put that over 1/2, but now notice that those 1/2 will just cancel, so they become irrelevant pretty quickly, but they still should be recalled and used as part of the definition. Let's continue on simplifying this using some familiar algebra and even some steps we already used above in a previous example. You'll note that e to the ln of x reduces to just x. So our first term in the numerator is just an x. Then we have a minus. The second term, we're going to use this little trick we did above. So instead of e to the negative ln of x, we're going to rewrite that as e to the ln of x all to the negative 1 power, which is just a little algebraic trick to get it more concise to us. E to the ln of x is what we want to be able to simplify, and we'll do that quickly next. Down below in the denominator, some similar things happen. We have e to the ln of x as our first term. Well, that's just x. And now we have a plus, given the definition for cosh. Here we have a plus. And then similar trick, we'll call this e to the ln of x, all to the negative 1 power, to represent that second term of e to the negative ln of x. And we can reduce a little bit more, so let's do that. I'll continue on. In the numerator, we're going to have the x as the first term, then a minus. For the second term, e to the ln of x reduces to just x, but now it's really x to the negative 1, given that power that we introduced there, or just kind of used to rewrite the expression. Similarly, down below, we'll have x, and then plus e to the ln of x is just x, but it's to the negative 1 power. We can simplify this a little bit more. If you go back to some algebra, this is really just x minus 1 over x in the numerator over a denominator of x plus 1 over x. This is a complex fraction from beginning algebra even, or intermediate algebra. And so we could simplify it by multiplying numerator and denominator by x, which we'll do here, which is a just convenient form of 1. So we can do this algebraically and end up with, if you distribute this x inside, you'll get on the top, or numerator, x squared minus 1. Down below, x squared plus 1, which, as you might recall, is exactly where we were trying to go. Go back and look at the problem. That's what we were trying to prove beginning to end. So when we get to the end of the proof, we put a little box to say we're done with it. And the whole string of logic is our answer to this prove question. All right, let's move on to another example. Our next one states this: if cosh of x equals 5/3 and x is greater than 0, find the values of the other hyperbolic functions at x. So this actually resembles a problem you might see in trigonometry. And remember, a lot of these hyperbolic equations or expressions or identities resemble some trigonometry. So we'll be able to leverage that, I think, to our advantage. We know that cosine hyperbolic of x equals 5/3, and we're going to use that as our building block. And we're told that x is positive, so we'll keep that in mind as well. Now, when being asked to find the other hyperbolic functions, we're talking about, sinh, tanh, cosecant hyperbolic, all those other ones we have defined above, and this information should be enough to do that. Now, notice we have cosh, which we could use directly to find secant hyperbolic by that definition. You may recall from trigonometry, though, that it's also helpful to know what sinh would be in this case, because all the other functions will depend on those too. Well, thankfully, we have an identity above that will give us the answer to that. So let's recall. I'm going to just kind of put this in here. Recall, we have an identity above that said that cos hyperbolic squared of x, so cosh squared of x, minus sine hyperbolic squared of x, so minus sinh of x, equals 1. So that identity, as we have listed above, is going to be a building block that will help us find sinh, given that we know what cosh is. And again, this is the one that kind of looks like the Pythagorean identity, but it's different. This one has a minus sign instead of a plus. It's easy to get those mixed around if you're fresh with some trig, so be careful on that. Let's plug in what we have then. So cosh squared of x. Well, cosh of x is 5/3, so if we put 5/3 squared to represent that first term, and then minus, and then sine hyperbolic, so sinh squared of x, we know that this equals 1. Well, let's do a little bit of arithmetic here. This means that 25/9 minus sinh squared of x equals 1. Let's see, if we do a little bit of algebra, like adding sinh squared to both sides and subtracting 1 from both sides, maybe write that out in detail if you need it, but let's kind of review then that sinh, so sine hyperbolic squared of x, would equal, again, so I'm just kind of moving the sinh squared to the other side and then subtracting 1 from both sides, doing the arithmetic involved for that. Sinh squared should end up being 16/9. Again, that's like, 9/9, with combined with the 25/9, just doing the arithmetic to get sinh squared by itself from the previous step. I didn't write every detail there, but you can try that on your own. Just some basic arithmetic there, moving stuff around. Now, I want to get sinh, so we're going to take the square root of both sides like we would have maybe in trig. So we'll do that, but you may also recall from trig or algebra that when you take the square root of both sides of an equation, you have to be careful. So now we're going to say that sinh of x being reduced with the square root from the squared, right, is going to equal plus or minus, and then the right side, the square root of 16/9 will reduce to 4/3. Of course, then we can decide based on the plus or minus from the condition we had earlier been given, which is that x has to be positive. And so we'll say sinh is the positive version of this, the positive 4/3. And so we'll box that up. Remember, we're trying to find all these hyperbolic functions, that being one of them. Of course, only the positive version is the one we're using there. We were given cosh, so there's no need to find that. But we want all the rest. So let's carefully walk through these using the definitions above. So for example, we also know that the cosecant hyperbolic of x would be 1 over sine hyperbolic of x, 1 over sinh, which we already found. So that means that cosecant hyperbolic of x in this context would be the reciprocal of the sinh we just found, which was positive 4/3. So this will be positive 3/4 for cosecant hyperbolic. Moving on, we also want to know what tangent hyperbolic of x would be. Remember, tangent hyperbolic of x would be sine over cosine, so sinh over cosh. Given the definition above, well, we know what those are now. So since sinh is 4/3, positive 4/3, and cosh is given as positive 5/3, we can do some algebraic reduction on those. The thirds would cancel in each case, giving us just 4/5 for the result for tang in this context. Moving on, we could also get cotangent hyperbolic of x, which is really just the reciprocal of tangent hyperbolic, so that will just be 5/4. Again, we're just kind of using the definitions that we have above, putting them together as needed here. Now, I stated above in our definitions, and kind of like trigonometry, if we remember back to that, we should end up with 6 results. It looks like I'm missing one. Let's see, 1, 2, 3, 4, 5. What am I missing? Oh yes, secant hyperbolic I don't have yet. Thankfully, it's not that bad. So we'll say here secant hyperbolic of x. Remember, secant is 1 over cosine, and the same way secant hyperbolic is 1 over cosine hyperbolic, which was the one that was given to us. So that would be the reciprocal of cosh, which in this case then would be 3/5. So we're just kind of taking the reciprocal of that given value to finish that one out. Now we have all 6 hyperbolic functions, and we're good to go. All right, and for our last example in this topic, we're going to find the derivative of g of t, which is given as a hyperbolic function. So g of t is defined as sinh, so sine hyperbolic, of the natural log of t. All right, so thankfully we have some derivatives defined above. You can go back up and review these as needed. They're somewhat familiar looking to us if you go back to some trigonometry also. And so let's do this. We know what g of t is as given. We want to find g prime of t. So let's write this out. G prime of t equals. Now notice a composite function. G of t is given as sinh of natural log of t. So as we know with calculus, with a composite function, we're going to have to use the chain rule here. So we'll start with the derivative of the outer function first, which in this case is sinh. Now go back up and review the derivative for sinh. You'll find that it's cosine. So we'll say here, the derivative of g prime of t, is going to be cosine hyperbolic. That is, I said cosine, I meant cosine hyperbolic of ln of t, the inner function. So there's the outer function's derivative. The derivative of sinh is cosh. But as stated, as we know, we have to now use the chain rule. So now we're going to multiply by the derivative with respect to t, our independent variable here, of the inner function, which is the natural log of t. So let's put this together. Our first factor is cosh of ln of t. But now we're going to multiply that by the derivative of that inner function, which happened to be natural log of t. Of course, with respect to t, the derivative of natural log of t is just 1 over t. See derivative rules in Calc 1, right? So we want to simplify this as much as we can, knowing the definition of cosh that we have written above. So let's do this. Using the definition of cosh as the fraction, remember it's e to the input, so e to the ln of t. And then it's plus e to the negative input, so an e to the negative ln t. And this is of course all over 2, so you could do that a couple different ways. I'm just going to put a 1/2 outside of those two terms contained in parentheses. So what we have here is simply the definition of cosh with the input of ln of t. So it's e to the ln t plus e to the negative ln t. And then it would be all over 2. So I'm accounting for that with a 1/2, or you could put it all over 2 as defined as well. And then that's times 1 over t. So I'm going to put that t down below. There's a couple ways to write this. I'll probably clean this up even more. So let's keep going. We could do in the numerator now, instead of e to the ln of t, we know that those reduce just to t. Then we have plus. We've seen this trick before where we have e to the negative ln of t, but if you rewrite that as e to the ln of t to the negative 1 power, then do the simplification there. That's really just t to the negative 1. So we'll write it that way, which is that second term. And then instead of writing the times 1/2 on the outside and then all over t, we'll just make that all over 2t, which would be an equivalent algebraic simplification to combine those two denominators. And we should take it a little bit further, so let's do that. Notice that we have a complex fraction lurking because our numerator has this 1 over t term in it, this t to the negative 1. So we could, let me write this out carefully. This is t plus 1 over t all over 2t, and we don't want to leave a complex fraction as a simplified result, so we'll multiply top and bottom by t, just using a convenient form of 1 here, t over t. To make this look a little better, if I distribute this t inside now, we'll end up with a t squared plus 1 in our numerator over a 2t squared in our denominator. And that's a more simplified result, which means we can leave it right there.